Have you ever really stopped to wonder how the device you're watching this on actually works? I mean, how does a chunk of metal, plastic, and glass do all the incredible things it does every single day? It turns out it all comes down to one single, incredibly simple idea. Let's dig in.
Think about it. Every single piece of modern tech we use, your phone, your laptop, your car, even your smartwatch, they all share a secret, a fundamental principle that lets them process information, crunch numbers, and connect you to the entire world.
And this entire universe of complexity, from sending a text message to rendering a complex video game, it all boils down to one simple choice that's just repeated billions and billions of times per second.
Yep, that's it. On or off, 1 or 0, true or false. This simple binary choice is the language of all electronics. But hold on, how do you get a piece of silicon, which is really just purified sand, to make that choice? Well, that's where the real magic begins.
Okay, so to understand that on-off switch, we've got to look at the material itself. It's not quite a conductor, and it's not quite an insulator. It's something in between called a semiconductor, and its unique properties are, quite literally, the foundation of our modern world.
Let's think of it like traffic lights for electricity. In a conductor, like a copper wire, it's a constant green light. The electrons can go whenever they want. In an insulator, like rubber, it's a permanent red light. The electrons are locked down, they can't move. But semiconductors, like silicon, they're special. They have a manageable gap. It's like a traffic light we can control. We get to decide when it's green and when it's red. We can control when the electrons are allowed to move.
To really get that idea of a gap, let's use an analogy. Imagine electrons live inside a building. The valence band is the ground floor. Down here, electrons are comfortable. They're bound to their homes, their atoms. They aren't really going anywhere or conducting any electricity.
Now, the conduction band, that's the floor above. Let's call it the mobility floor. If an electron can just get enough energy to get up to this level, it's totally free. It can run all over the building, carrying an electrical current with it. This is where all the action happens.
So how do electrons get from the ground floor to the mobility floor? They have to climb the band gap, which you can think of as a staircase. In an insulator, that staircase is miles high. It's impossible to climb. In a conductor, there isn't even a staircase. The floors are basically merged. But in a semiconductor, the staircase is just the right height. We can give an electron a little push of energy, and it can climb those stairs right up to the conduction band.
And here's the really clever part. This is how we take control. We use a process called doping. By adding tiny, very specific impurities into pure silicon, we can create one of two things. Either an excess of free electrons, we call that N-type for negative, or we can create an excess of electron vacancies, which are called holes, and we call that P-type for positive. So now we have two different flavors of silicon, and we can finally start building something useful.
So what happens when we put these two types of silicon right next to each other? Well, we create our very first, truly useful component, something that can impose some order on the wild flow of electricity. We create the diode.
When you join a piece of P-type silicon to a piece of N-type, you create what's called a PN junction. And this junction acts exactly like a one-way valve for electricity. Current can flow easily from the P side to the N side, but it's almost completely blocked if it tries to go in the reverse direction. It's a one-way street.
So why is a one-way valve so important? Well, the electricity coming out of your wall is alternating current, or AC. It flows back and forth, constantly changing direction. But our electronics, they need a steady one-way flow called direct current, or DC. A diode is the perfect tool for the job. During the positive part of the AC wave, the diode's valve opens and lets the current through. But during the negative part, the valve slams shut. What you get is a pulsating current that now only flows in one direction. We've taken chaotic energy and started to tame it.
Creating a one-way street is cool and all, but the real revolution, the real game changer, came from the next component we built. It is, without a doubt, the most important invention of the 20th century. It's the device that finally gave us that perfect on-off control we were looking for, the transistor. Just to give you a sense of scale here, I want you to try and wrap your head around this number. Humans manufactured roughly 2 sextillion transistors in just one recent year. That number it's basically impossible to comprehend. It's more than all the grains of sand on every beach on Earth combined. These things are the microscopic, invisible heartbeat of our entire civilization.
So how does this tiny thing work? You know what, the best way to think about it is just like a water faucet. A transistor has 3 connections: the collector, the base, and the emitter. The collector? That's like the main water pipe, full of pressure. The emitter is the spout where the water comes out.
And the base? The base is the handle. A tiny, tiny little turn of that handle, which is like a small electrical current, can control a massive flow of water, or current, from the collector to the emitter. It's a switch, and it's also an amplifier. It's brilliant.
Okay, this is where it gets really fun. We have a switch, a very, very tiny and very, very fast switch. So, what do we do with it? Now, we teach it to think. By arranging these transistors in clever ways, we can create circuits that make actual logical decisions. We call these logic gates.
First up is the AND gate. This one is the strict gatekeeper. The output here will only be on if input A is on and input B is on at the exact same time. If either one is off, or both are off, the output is off. Simple as that.
Then you've got the OR gate, which is way more relaxed. The output here is on if input A is on, or if input B is on, or if they're both on. The only way you're getting an off at the output is if both inputs are off.
And finally, we have the easiest one of all, the NOT gate, or inverter. It does exactly what it sounds like. If the input is off, the output is on. If the input is on, the output is off. It just flips the signal.
You know, that AND gate is really just like a nightclub bouncer. You need your ID, and you need to be on the list. If you're missing either one of those things, sorry, you're not getting in. You need both.
All right, now for the final leap. These gates, AND, OR, NOT, they are our basic Lego bricks. By themselves, they're simple, but when we start combining them, we can create circuits that perform any logical task or mathematical calculation you could possibly imagine.
This is where it gets incredibly powerful. We can take abstract math and turn it into a physical circuit. Take a look at this expression. It might look complicated, but we just build it one piece at a time. First, we see C and D, so we just feed inputs C and D into an AND gate. Done. Next, we need to OR that result with B, so we take the output from our first gate and run it through an OR gate with input B. And finally, we take that entire result and run it through one last AND gate with input A. And there you have it. We've built the expression in hardware.
And that's the whole journey right there. We started with silicon, which is basically sand. We doped it, gave it special properties, and used that to build a transistor, the perfect switch. Then we arranged those switches into logic gates that can make simple decisions. And finally, we combine those gates to perform complex calculations.
And really, that's the secret. Every photo you take, every song you listen to, every digital world you explore, it's all built on that one simple choice, on or off, executed by billions of microscopic switches, which leaves us with one last, really fascinating question. If this is what we can build with simple on/off switches, what comes next?